Hi everyone, in this video we will be completing the remainder of section 15.6. In class we left off in the middle of an example where we had to find the centroid of a region. We already established that y bar is equal to 0 because it's symmetric above and below the x-axis. Okay, we wrote down both double integrals in class, so I'm going to take the time now just to solve one of them, but not both. And the one that I'm going to start with is the mass integral, so the denominator of that fraction there. So my mass integral is the integral from 0 to the natural log of 2, and I'm going to take the antiderivative with respect to y because my function is just 1, so antiderivative that would be y, and then I can just plug in top bound minus bottom bound right off the bat here because I'm just substituting into a y. So we have e to the negative x minus 1/2 for the top bound minus the bottom bound 1/2 minus e to the negative x. Still have my dx there, and that simplifies a little bit. 0 log 2, that's 0. That simplifies a little bit. We have e to the negative x minus negative e to the negative x is 2e to the minus x, and negative 1/2 minus 1/2 is minus 1, and then dx. Okay, so our antiderivative of that is negative 2e to the negative x minus 1x, and that gets evaluated from 0 up to the natural log of 2. Then we substitute in top bound minus bottom bound again, and what do we end up with? Let's see. And we get negative 2e to the negative natural log of 2 minus the natural log of 2 for the top bound substituted in. And then the bottom bound, be careful, there is a term there. E to the 0 is 1, so my bottom bound is minus is negative 2 times 1, and I'll write the times 1 also. And that would be because of the e to the 0 term. So we do have a bottom bound there to be aware of. That all simplifies. E to the negative log 2, that would be negative 1/2, because the negative in front of the log 2 you can bring it up as an exponent. But what that ends up simplifying, and you can check and make sure you get that in your calculators, 1 minus the log of 2, or approximately 0.30685 when you actually type it in. Okay, so that one's kind of ugly. So that's the mass of that region. Then to compute m sub y, the moment about the y-axis, so for that I'm looking at the numerator. What you end up with, because of the x there, the first integration is straightforward because it's the dy, and then you take the antiderivative, so we'd have x times y, plug in top bound minus bottom bound. What you end up needing to do is an integration by parts, which would take a little bit. So, I mean, we could do the integration by parts, or you could look up a formula in the back of the book using the table. But for the purposes of this video, I'm going to save a little bit of time and write down the answer. But again, I went through one. The other, you'd have to use an integration by parts. So our m sub y integral is equal to, that one is decimal point 0.06663. Okay. Well, actually, that one's approximate, not equal. So that's what you would get if you went through the integration by parts and went through the whole integral. Okay. So now our last step here is x bar is equal to m sub y over the mass. And that is approximately, well, let me write in my values here, 0.06663 divided by 0.30685, and that is approximately 0.2161. Okay, so we have the coordinates of the centroid are 0.2161 on the x-axis and 0 on the y, and that gives me the coordinates of that point right there, the center of mass of that kind of triangular shaped region. In this next example, we're told to find the centroid of a region where we're given a density function this time. And again, half of the problem is relatively straightforward because we're symmetric now over the y-axis. The x-coordinate of the centroid, x bar, is equal to 0. Okay, so we've got to find y bar. which is equal to the moment about the x-axis divided by the mass. And we've got to do two separate integrals, one for the mass, one for the moment. This region is easier to work with because it is symmetric. So when I find my mx, the moment about the x-axis, or I said because it's symmetric, I mean because it is rectangular, I can write my bounds are from -1 to 1 on the x-axis, from 0 to 1 on the y-axis. Again, because it's just a rectangle, of y, because we're finding the moment about the x-axis, times 2 minus y, the density function, dy dx. So I chose to write my y bounds first, then my x bounds, and again, the setup for this one is better than the last one, easier than the last one, because it is a rectangular region. Okay. Then, evaluating this integral, we have -1 to 1. We get 2y when you distribute the y, so it'd be 2y squared over 2, or just y squared, minus 1/3 y cubed, again because you're distributing and then taking the antiderivative. That gets evaluated from 0 to 1 dx. And then what do we end up with here? -1 to 1. Top bound is 1, so I have 1 minus 1/3. Bottom bound is definitely 0 dx. And 1 minus 1/3 is 2/3 times, now I'm going to take my antiderivative in terms of x, which would be x, evaluated at 1 minus -1. That simplifies to 2. 2 times 2/3 is 4/3. Then for our mass integral, the bounds are the exact same. The integral is the exact same. The only difference is I don't have that factor of y inside of my integral. So the density function 2 minus y, bounds are the same, dy, or order of integration is the same, dy dx. Now I don't have to distribute anything, so I have 2 times y minus y squared over 2, and that gets evaluated from 0 to 1 dx. And then when we substitute in our bounds, 2 from the first term, 2 times 1, minus 1/2 from the second term. Y squared over 2 would be 1/2, and that's dx. 2 minus 1/2 is 3/2, and then similar to the last problem, now it's just a constant integrated with respect to x. Constant times x, evaluated at 1 and -1. That's 2. So we have 3. Okay, I know I went through that part a little bit more quickly, but go back, watch it again, or maybe you can slow the YouTube video down and listen to me in slow motion, which probably would be terrible. There's our two integrals that are going to give us our y bar, the y coordinate of the centroid. So we take our first answer, 4/3, divide it by our second answer, which is 3, and then you get 4/9. Okay, so the centroid for this rectangle with variable density is 0,4/9, and so it would put us, I don't know, right about there, slightly less than halfway up, because the rectangle is, if you think about that density function, 2 minus y, it is least dense at the top, 2 minus 1 is 1, and most dense at the bottom, 2 minus 0 is 2. So the density, it pulls the centroid down the rectangle a little bit further. Now in the last part of the section, we're going to look at the centroid in 3 dimensions, and that of course gets much more fun. We have to compute an x bar, a y bar, and a z bar when we're working in 3 dimensions. X bar has a moment about the yz plane, y bar has a moment about the xz plane, and z bar is the moment about the xy plane. Okay, most of the time the regions are going to be symmetric so that you don't have to do as many integrals, because in 1 dimension, let me write this down, in 1 dimension we need to evaluate 2 single integrals. 2 single integrals. But in 2 dimensions, remember the problem we just did, if we had an x and a y coordinate, we need 3 double integrals, 1 for the x, 1 for the y, 1 for the mass, Great handwriting here. And then in 3 dimensions, we have a mass, an x coordinate, a mass, a moment about the yz plane, a moment about the xz plane, and a moment about the xy plane. So we have 4, and because again 3 dimensions, triple integrals. So these problems can get real fun if they're not symmetric. Here is our definition, our formula slide, but hopefully you can kind of see, or you can kind of maybe predict what's going on here. When we compute x bar, our triple integral has an x in it. When we compute y bar, our triple integral has a y in it. And then when we compute z bar, triple integral has that extra factor of z in it. And then the mass integral, at the bottom there, that one does not have an x, y, or a z, just the density function. And again, when you do examples of these problems in 3 dimensions, look for symmetry. There will hopefully be symmetry to make the problem less terrible. The last example that we're going to do in this section involves the center of mass of a constant density cone. So we're given this cone and we need to find the center of mass. The thing to initially notice is the symmetry. Our region is certainly symmetric over the xy plane. So our x bar and our y bar is equal to 0. So see, two of the triple integrals you don't even have to worry about. But we do need to find z bar. Okay, how high up the z-axis is that center of mass? So z bar, that's the moment about the xy plane divided by the mass. And I think I want to do my mass triple integral first. So that would be the integral over our domain of the density function, rho of x, y, z, dv. Okay, so let's just talk about a couple of pieces to that here. First, the rho, now it says that I have a constant density cone. Well, that's good. That means that my rho function is just 1. So that's going to simplify things a little bit. And then when you look at the region, right, it's kind of round. It's a cone. So even if I wasn't given this information here at the bottom, I would still want to do this, set up this integral in polar form. So now as we move through the remainder of this chapter and then even into the next one, you kind of have to choose when it's best to set things up in polar and when it's best to use rectangular and when it's best to use spherical as well. Okay, so our mass integral, since we know we're going to do polar, our theta bounds are from 0 to 2 pi, because it's the whole way around. Our r bounds are from 0 to 4. That cone intersects the xy plane at a circle of radius 4, and you can see that in the picture. The circle is of radius 4. And then the z bounds are from 0 up to 4 minus, well, the cone has the equation z equals 4 minus radical x squared plus y squared, which would just be 4 minus r when we convert it to polar. Okay, so that's going to, again, make things a little bit easier to work with. And then our differentials, dz, r, dr, and d theta. And again, if you like to write the 1 in there, I sometimes will. There's a 1 there as the coefficient, or as the function. Now, we take our first antiderivative with respect to z, top bound minus bottom bound, and you get 4 minus r. R, dr, d theta. Okay, I'm not going to go through the entire rest of this integration. You would distribute, take the antiderivative, and then just it becomes calculator work. But what you should end up with is 64 pi over 3 for the mass integral. So my mass is 64 pi thirds. Okay, now the next step is our moment about the xy plane, and that is a triple integral with an extra factor of z in it. Z and then dz, r, dr, d theta. The good thing about this one is I don't even need to think about the bounds. 0 to 4 minus r for the z bounds, 0 to 4 for the r bounds, 0 to 2 pi for the theta bounds. They're the same as the previous integral. Okay, this one, it's a little bit more complicated to work out because my integral with respect to z is now z squared over 2. So after the first integration, we have 0 to 2 pi, 0 to 4, and then it ends up being 4 minus r squared over 2 r dr d theta. So there's a little bit more, this one gets a little bit messier. We can factor the 1/2 all the way out in front of the integral, and I'm just going to do one more step here and then write down the answer. So I can factor my 1/2 out, which then is going to be, look like this. Whoops. It's going to look like this. So this equals 1/2 the integral from 0 to 2 pi, 0 to 4. And then when you square that binomial, it's 16 minus 8r squared plus, 16 minus 8r plus r squared, which would then get the r distributed to it. So we have, after you distribute and simplify, r to the third minus 8r squared. That's what I mistakenly wrote a minute ago. Then plus 16r dr d theta. So I'm not, it's not r dr d theta. I already distributed that. Okay, so this, again, just a little bit messier with what all of our terms here, but what you end up with, similar to the last example, actually exactly like the previous integral, is 64 pi over 3. Go through the last two steps there and focus on your calculator because there's a lot to keep track of. You do get 64 pi over 3 for both the mass and the moment. So that when I go back up to my formula there, if I put 64 pi thirds for the moment divided by 64 pi thirds for the mass, divide them, you get 1. So apparently the center of mass, or the centroid of that cone with a constant density, is 0, 0, 1, and that's what I've got over. Oops, that's what I've got over there in the picture too. The center of mass is at 0, 0, 1, which is kind of interesting. So a cone, that cone has a height of 4. The center of mass is 1/4 of the way up the cone. Okay, that's it. That's the end of the section. If you have questions, please come to class with them, email me, see me in my office, but that is where we are going to stop for this section. Thank you for listening.